Okay, that will do it. The thing is, in these equations, x is an ordinary variable. So if we were to take the derivative, for instance, with respect to x of x to a power, maybe. You bring the power down, raise it to 1 power less, just like you normally do. But if you were to take the derivative with respect to x, say of y to a power, now y is a function of x. So you get the ordinary derivative, power, times the derivative of the y. Since we've got the chain rule going on there, because y is a function of x. So here's an example. I would like you to find the derivative. Find dy dx or y prime, whichever notation you like the best. If the equation given is 6x squared times y cubed plus the tangent of y is equal to the sine of x. So pay attention, it looks like an equation instead of a function. You know, it didn't have f of x is equal to, just has an equation over here. Then the other thing you have to pay attention to is that first term. I've got a 6x squared y cubed. That's 6x squared times y cubed. So you've got to do the product rule right there. The other ones are just individual terms, but make sure you recognize that this involves the product rule. Okay, let me kind of play along here. I'm going to do the product rule right here. So I've got the first, come on, pen, times the derivative of the second. So like I said up above, you just take the ordinary derivative, but then you tack on y prime. I'll use the y prime for now. When we go in the next section, I'll use the d whatever notation. That's half of the product rule. And then the other half of the product rule is the second times the derivative of the first, and that's just 12x. Then we move across and take the derivative of the tangent of y. First, the ordinary derivative. The derivative of the tangent is a secant squared. But now we go inside and take the derivative of the y, we get y prime here. And then we have to move across the equal sign and take the derivative of the sine of x. And so across the equal sign, the derivative of the sine of x is just the cosine of x. So our derivative is embedded in an equation. The rest here now involves simplifying this and solving for the derivative term. Are you okay with all the steps here? Can you need me to go back and point anything out? Okay, so I'm going to keep this term over here and that one. And I'm going to move this over to the side of the equal sign with the cosine. I'm going to go ahead and put this together, make that 18x squared, y prime. And then I'm going to make this secant squared y times y prime right here. Then I've got the cosine of x on the right-hand side. And when I move this over, I subtract it and get 12xy cubed. And we keep our y prime terms together. So that I can factor them out in the next step. So pull out a y prime right here. And that leaves me 18x squared y squared plus the secant squared of y. And on the right-hand side, I still have the cosine of x minus 12xy cubed. And then I divide by the step in the parentheses and we have y prime. And this still has the same interpretation as before. You can use this to measure an instantaneous rate of change, such as the slope of a tangent line. Okay. So let's do a tangent line problem. Write an equation of the tangent line. To the graph of 4 over x plus 10 over y squared is equal to 6 times xy at the point when x is 2 and y is 1. Yeah, that's the point on the graph, right? Write an equation of the tangent line to that graph at the point 2, 1. So you're going to do the same thing. You're going to take the derivative all the way through and you're going to get some equation like this. But then you can skip the step where you solve for y prime. You can go ahead and put the numbers in right here. And that might make it easier for you to solve for y prime once you get to this line. Let's see, can't see that. Let's move it. Move it, move it, move it. Okay. Any luck? Anybody have a number for the slope so we can check our answer? Well, I take the derivative, I'm going to rewrite it. It's 4 times x to the -1 plus 10 times y to the -2. And then I can just do the power rule over there. You guys doing the product rule on the right-hand side? Good. Okay, so we take the derivative of each term. The first term has as its derivative -4x to the -2. The second term has as its derivative -20 y to the -3 times y prime. And then on the right-hand side, we're going to do the product rule. 6x is my first term, y is the second term. So it's the first times the derivative of the second. Well, the derivative of y is simply y prime. And then the other way, the second term times the derivative of the first. Derivative of 6x gives me the 6. And now I'm going to write with positive exponents, and then I'm going to put the numbers in. So this becomes -4 over x squared minus 20 over y cubed times y prime. And then this stays the same. Now I'm going to put 2 in for x and 1 in for y. And we'll crunch the numbers out. 1 cubed is just 1, 2 squared is 4. And so I get -4, oops, sorry, -1 minus 20y prime is equal to 12y prime plus 6. And now we can put our y prime, yep, what you need.
Would it have made a difference, like in this step, if I've already like moved the x's and y's to one side and the y primes to the
Yeah,
other?
that wouldn't matter. We'll see. We'll see if we get the same number. I'm going to put my y primes over here. And I'm going to move the 1 to the other side. So -20 y prime minus 12 y prime gives me a -32 y prime. And then I'm going to add 1 to the 6 to give me a 7 over here. So did you get 7 over -32? And your slope of the tangent line? All good? And the rest is just point slope formula. Y minus y1 is equal to m times x minus 1, x1. So y minus 1 is equal to -7 over 32 times x minus 2. It's the equation of the tangent line. Okay. Got the same answer. Then it works. Then it works, by gosh, by golly. Okay, the next thing we did is we took higher ordered derivatives. Let's see. Find both y prime and y double prime in terms of x and y if y is equal to, I don't want y is equal to, if 2x plus y to the third power minus x squared is equal to, I don't know, how about y to the second. It's gonna be a little bit messier to get y prime, maybe. We'll see. Maybe put too much fluff on this one. We'll see. You can handle it. Let's make sure we all get the same first derivative before we take the second one. Okay, so I'm gonna catch up with you here. I'm gonna do the general power rule, bring the 3 down, leave this all alone. Raise it to the second power. Now we go inside and take the derivative of each term. Derivative of 2x is 2, the derivative of y is our y prime. And I'm here taking the derivative of the minus x squared to get a minus 2x. And across the equal sign, I get a 2y y prime. Okay, so this is all one term right here. That's all one term. But I can break it up into 2 terms if I distribute this through the parentheses. And that's what I'm going to do next. I'm going to take all of this and multiply it by the 2 and get 6 times 2x plus y squared. And then I'm going to take all of that and multiply it with the y prime. So here's the plus sign from here. And then I get that same batch in the parentheses. But now it's multiplied by y prime. So treat that as something, and I'm distributing it through the parentheses. Did you want to do something else? You're looking at it funny.
Can you explain that again?
I'm trying to get this y prime out of here, but it's embedded in the parentheses. So I'm going to work to get rid of these parentheses. These parentheses are holding multiplication by this term. So I'm going to take that term as one blob and multiply it with the 2, and then that term and multiply it with the y prime. So when I multiply it with the 2, I just get a 6 times that, and then I multiply it with the y prime. So now I don't have anything, the y prime is outside of the parentheses. And I'm going to put my y prime terms on the left-hand side and put my non-y prime terms on the right-hand side. So I'm going to move this one over by subtracting it. I'm going to move that one over by adding it. And that one over by subtracting it. So how much of this makes the tilt it in here. Okay, so I'm keeping this term over here. Let me write it first. 3 times 2x plus y squared times y prime. Then this is going to join it, so I'm going to have a minus 2y y prime. Moving this one over, it becomes a positive 2x. Moving that one over, so it's a minus 6 times 2x plus y all squared. And once you get the y prime terms by themselves, you can factor out the y prime. If I take the y prime out of here, I have the 3 times 2x plus y all squared. When I take the y prime out of here, I just have a minus 2y. Everything is the same on the other side. And the next thing I'm going to do is divide by the stuff that's in the brackets. And I've made too big of a mess. So you might have to just truncate this problem. I need an easier one to find the second derivative of. So y prime is going to be the stuff on the right-hand side, 2x minus 6 times 2x plus y. And I believe that is squared all over the stuff in the brackets over here. So I'm not going to do the y double prime for this one. This is going to be too messy. I gotta make it easier looking problem. Because in the second derivative, every time we get a y prime, we would have to substitute that in, and that's too much to write. Here, okay, here. This one? Which one? This one to that one?
No, like when we were trying to take out the y prime.
I only took out the y prime from here to here. So if I'm pulling out a y prime, there it is. 3 times 2x plus y squared is here. Minus, and I'm taking that out. And so I have 2y there.
I was just confused like from the top in the 2 plus y prime, and then you have but on the next one 3 times 2x plus y squared times y prime. I think it's what I understood. Yeah.
Oh, that's the distributive property. That's taking this term here. This term right here. And I'm sending it through the parentheses. So that I can get rid of these parentheses. So I take that times 2 to get 6 of them. Then I take that times y prime to get it over here. Okay. So here we're distributing.
Just left as like one instead of like doing each individual.
Because these parentheses right here were giving me trouble. I need to get the y prime out of there. I could have divided, but then this would have a denominator and that would have a denominator. So I didn't divide right there, I factored, or I distributed.
The reason it confused me is because I've never seen something distributed like that. Like, whenever people said distribute, I would thought like in the parentheses, so like the 2 and the 2x and then the 2 and the y.
Oh, yeah.
Just kind of-
Yeah, but I couldn't because this is protected by the power.
So you just left as like one term, as if we're like distributing 3 into the
Yeah,
parentheses.
Blah goes through the parentheses. So red box times 2, red box times y prime.
If you think about like you replace the parentheses with an x, it's 3x squared. You
Right.
just distribute that.
Yeah.
I had just never seen that, but now.
Maybe we should do more like that. See if we get another one that does something. Maybe we should do one more like that one. Okay, so let's do the same thing. Find y prime. Okay, so what made that look like that? Guess the parentheses. Let's go with the sine of y plus the cosine of x. Let's put it to a power. Let's go to the fifth power. Is equal to 2 pi times y. Just two. I have a number. I have a number too. Good. Good. So if you got to here, there's the power rule. Bring the power down, raise it to 1 power less. Now we're inside. We encounter a sine of y whose derivative is the cosine of y. Now we take the derivative of that y and get a y prime. We'll move over here, take the derivative of cosine of x, it'll be a minus. Let me go ahead and put a minus right there, sine of x. Then on the right-hand side, I've got a number times y, so the derivative is just that number. But now we take the derivative of y and get y prime. So 2 pi y prime is the derivative on the right-hand side. So you see how we've got the distribute stuff again? My y prime is stuck in here inside this pair of parentheses, so I need to get rid of them. So the thing that's acting as the term that I'm going to distribute is all of this. So that's one chunk. Take that chunk and I'm going to multiply it with this. Then I'm going to take that chunk and multiply it with that with a minus sign in between them. Have you done that part yet?
No.
Try it. All right, I got you guys for the extra hour today. So here goes that underlying term times the cosine of y prime. I'll just keep it in that same order. All of that times this term, so that gives me cosine of y times y prime. Now I'm going to take that red underlined term and multiply with minus sine of x. So I'm going to put the 5 sine of y cosine of x all to the 4th, and now it's multiplied by that sine of x. Right?
Yes.
Yes, sir.
Two questions. So is it okay if we put the cosine y prime with the 5?
Sure.
Okay, and then also, the reason that we're doing this is because it has the to the 4th power, right? To the power. So let's say if it was 5 sine y plus cosine x times the cosine y prime minus sine x.
Uh-huh.
Would you then distribute?
Yeah, you can
Like-
foil it out.
Yeah.
then.
Well,
Yeah, you could do that.
or I'm sorry. Could you also do what we just did so that it would be easier to factor out?
Yep. Oh, yeah, I lost it. You're right. Good eye. Right here. Is it gonna fit? Isn't that what you're here for? Okay, let's get our y prime terms together. So I'm going to leave that there, pull that over, pull that over. So we have 5 sine of y plus the cosine of x all to the 4th, cosine of y, y prime, minus 2 pi y prime. And that moves over, becomes plus sine of y plus cosine of x to the 4th. Happy with that? Oh, I thought I shut that off. Away. 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 Did I just say I was in class? Okay, yes, I'm in class, standing here right now in front of everybody. Should I put you on speakerphone? Okay, I'll talk to you in a bit. I've got class for 3 hours here. I don't think that's a good idea. Okay. I always want to answer in case it's an emergency, and I didn't blow him off, but it was not an emergency. Okay, I'm going to factor out the y prime. I'm going to do it with this little rag. Yes.
What happened to sine x when you moved it to the other
Did
side?
I do something too? I did. Now it's back.
Yes.
Okay, I'm going to factor out the y prime by doing this. Feel free to do that too. And then the last step, I'm going to divide by what's in the box. And probably lose a few terms along the way. Ready, remember everything? So give me a reason that I cannot cancel the 5 sine of y plus cosine of x to the 4th.
This is a minus.
Because of this guy right here. It's not a common factor, so it doesn't belong to him, so I can't cancel it just because it looks alike. Okay? I know, there's that temptation. Fight that urge. Okay, so these can get messy. But this was just for entertainment purposes. I would never give you a messy one on the test because then I'd have to read through it. And we all saw how easy it was to lose terms. Okay, so let me find an easier problem to do a second derivative with. Find y prime and y double prime in terms of x and y if 4x y squared is equal to 6x plus 10. How about that? Should have put a y over there. I think it's perfect. It's perfect. Okay. Which was first. So I hope you see the product rule on the left-hand side. Let's all meet up with the first derivative before we take the second. Make sure we get to there in the right way. Okay, so I get the same y prime as you. I'm doing product rule. So here's the first times the derivative of the second. So the derivative of y squared is 2y prime. And then plus the second times the derivative of the first. And then across the equal sign, the derivative of 6x plus 10 is just 6. Are we in agreement to there? Then what did you do?
I moved 4y squared to the other side.
Okay. Did you go ahead and multiply these out? Get an 8xy prime. And the next step?
Draw one.
Good? Yes,
Did I reduce that?
you can. Everything's divisible by 2. You're into that. Let's knock out a factor of 2 everywhere. So 2 times 3 is 6. 2 times 2 is 4. 2 times 4 is 8. Okay. So how do you find y double prime?
Do it all again.
Again, from there, right? And from there, you're going to do what? Quotient rule. Question?
I don't know if this is a good one, but is there a way to change that fraction? Like, to make it 3 over 4yx and then minus 2y squared over 4x.
Yeah, you can split it up into 2
Yeah, and then,
fractions.
so you don't have to do the quotient rule, like, would that work?
Yeah, if you want to break that up, you can. But just for fun, we haven't done a quotient rule yet.
Yeah. I just don't like it.
Well, that's not what I asked.
I know.
It's the only rule we have that has a little song.
I figured out mine from high school.
What was yours from high school?
I remember my classmates would make fun of me because I would always say high first because it's low D high minus high because I
Right.
go over low low.
Okay.
And I would be like, my teacher would be like, Cassie, 'cause I could not remember. I don't know why. And I was like, hi. And everybody was like, whoa, oh, he's low first. And I was like, dang it. So now I remember.
It wouldn't rhyme if you did it high first.
I know. I got it stuck.
Songs gotta rhyme. Okay, doing quotient rule. The y double prime comes from taking the derivative over here. And then we're gonna do the bottom times the derivative of the top, minus the top times the derivative of the bottom, over the bottom squared. High D low minus low D high. Over low low. Sure, I shut that off this time. So you're, after you do the quotient rule, you're gonna have an x, y, and y prime on the right-hand side. Right? We're gonna get rid of that y prime by putting this in where the y prime is.
You're a genius.
I didn't invent it, I just write it.
Explains why I screwed up like 10 of them. I was about to do that, distribute.
Oh, well, we're not gonna simplify. All right, so here's what it looks like. The bottom is the 4xy. The derivative of the top. You tell me, what do you use the derivative of the top? Good. Negative 4y, y prime. That's the derivative of the top minus the top. And now the derivative of the bottom. Product rule, good eye. You want to continue with it?
So it's 4x. And then it's just y prime.
Okay,
And then plus, I think it just multiplies to 4y.
good. And then all of that is over the bottom squared. Okay. Okay, so what I'm going to do is write this first term as negative 16 xy squared times y prime, but I'm not going to put the y prime. I'm going to leave a gap there because I'm going to put this in those parentheses. I'm not going to do anything here. I'm just going to copy it down again. But right here next to the 4x, I'm going to put in my y prime expression again. And then on the bottom, I'm going to multiply that out and get 16x squared y squared. So I left parentheses wherever the y prime was before. And in those two places, I'm going to put this fraction. Yes, ma'am.
So, you know, like in the quotient rule, it has minus, right?
Right,
That means to like distribute the minus on everything to the right.
correct.
So not putting brackets like in all of that, does that still mean that you would distribute the minus with both of them? Like both of the parentheses?
I wouldn't. You could make that a plus, plus, minus, and that's it. You don't put it in here. Because that would be like putting a minus times a minus, and that's a positive. So don't distribute it. Let's leave it there. You happy with that answer?
Kind of.
Kinda, I know, I knew there'd be somebody who'd want to simplify. Really, the only thing I would do is, I would divide this into that, and I would cancel the 4x there, and then I would just stop, because there's just too much. There's too much to do.
We're chilling.
You chilling? But now that I said it, I probably should do it.
It's okay. Like,
4xy into that gives me negative 4y here. And 4x into that gives me that. Let's negative 4y times 3 minus 2y squared minus 3 minus 2y squared times the quantity 3 minus 2y squared over y plus 4y over the denominator. Yeah, I know. You made me do it. I was gonna stop. But I could tell that you were looking at it like, can we do more? As long as it's ready to be typed into WebWord.
Me and Tammy were saying that we were thinking of inventing or going to work for CEO and like giving him what would you say? I don't know. We're gonna invent a scanning feature on WebWork.
So that it can read your scan.
Yes,
That's
and
not a bad idea.
make.
That's not a bad idea. I don't know that that
I'm
WebWord
just
is
kidding.
a lucrative venture.
I'm not gonna complain too much about WebWork because at least you don't have to pay like $80
Oh,
to access it. So I'll take it.
That's right.
For a public speaking class, I had to pay for like 2 different website names just to turn in my stuff on one and do homework on the
How
other.
about a $400 art appreciation textbook for an engineering major?
I had to pay $50 for like a weightlifting access code last semester.
To access code,
Yes.
weight lift?
Yes. Yeah.
Really?
I wasn't about to pay $100 for a book I know we're not gonna read for a yoga class, so.
So you
I
dropped
said,
it?
bye.
So that means you didn't buy the calculus book.
No, I bought it.
Good. 'cause you've got three
Actually, I
cents.
did it. My brother took this
Good,
class. so-
good. Thank God for brothers. All right, you need to stand up, take a restroom break for another hour?
Yep.
Okay, go take a break. Make it quick.
Sorry. And then.
The X went out with the 4x on the bottom. So 4 goes into the 16 to give me negative 4. That X knocks that X out. And Y took one of those out. I know, it's like mathematical hazing. Now simplify. Let's see what we're gonna do next. We still got a bunch of stuff in this section. I just can't get all of that in one screen. This is feature not working. Yeah, we don't want to see this anyway. We don't want to see the simplified stuff. There's a random thought.
As a left-hander.
No, actually, it's so irritating. It always smudges.
Yeah, I like highlighters for like the color of them, but like actually highlighting things, it always gets messy.
Yeah.
Heather's just
And
color with tape.
cater to right.
Unless you're in Major League Baseball, then you get the money. So my son's always said, Mom, why didn't you let me be left-handed? Like, I stopped them from being left-handed. It's like I didn't let you grow real tall.
I tried to change my brother last year when he was born, but he just kept switching it up. Small.
We're going to use implicit differentiation to derive formulas for the 6 inverse trig functions. Yes. You forgot?
Oh, yeah. You know how I want to teach that.
You do? Like to kids?
Do what?
To high school kids? Oh, so
Anyway, so I already forgot. I forgot what I was gonna say. Oh, wait, okay, yeah. So like, I really like math.
okay.
So like, I enjoy memorizing like, the way I view it is kind of like, that does this, that can do this, like, and I can do these 2 things and I'll do this one, if that makes sense, I don't know. But the thing that I have trouble with is remembering the names of the stuff that I'm doing. So like implicit differentiation, like, I think I can remember that because I just thought of remembering it, but like, I
Okay.
know what to do, but I don't know the name of what I'm doing.
I understand that. That comes with time.
And that's what I need to
That
practice.
comes with time. You never really learn something until you do it in the next class. Then you'll know what it is.
Because like, when we started doing derivatives, like, I remembered how to do them, but whenever you said derivatives, I'm like, I don't remember what that is, but I knew how to do them, you know?
Okay.
Does that make sense?
Okay.
But now I remember,
Well,
like, the name of it.
okay. I'm gonna write down the 6 inverse trig functions. So y is equal to the arc sine of x describes an angle that we take the sine of to get that number x. Sine of that angle gives us back x. And we restricted those angles to be in a certain range. For the sine, it was minus pi over 2 to pi over 2. Then I'm going to write the same version for the inverse cosine. Y is equal to the arc cosine of x if and only if the cosine of y gives us back x. Now for the tangent, y is equal to the arc tangent of x if and only if, you have to save some room here, the tangent of y gives us back x. Let's see, then we got y is equal to the arc secant of x if and only if the secant of y is x. 1, 2, 3, 4. I got 2 more. Will they fit over here? Y is equal to the arc cosecant. Cosecant, I need to see. Cosecant of x if and only if the cosecant of y gives you x. And then finally, y is equal to the arc cotangent of x if and only if the cotangent of y gives you x. There's our 6 inverse trig functions. All right, I have to move my camera when I get these done. out. It just won't zoom out. Oh, well, I'll move those over when I get to them. So what I'm going to do here, in order to find y prime, I can't do it from this line. I'm going to find y prime from this line using implicit differentiation. So my goal is that if y is arcsine of x, then what is y prime? Okay, don't have a rule for it, so I'm going to go over here to this equivalent statement, take the derivative of both sides, and then I'll solve for y prime. So we're going to use implicit differentiation on this. So I'm over there taking the derivative of the sine of y, and what do I get? Cosine of y times y prime. Then I move over here and I take the derivative of x and I get 1. And now I'm going to solve for y prime. Y prime is 1 over the cosine of y. But I can go further. I can write the right-hand side as a function of x. If I know the sine of y is x, then I can figure out what the cosine of y is as a function of x. Because sine squared plus cosine squared is 1, right? But instead of doing it that way, I'm going to draw a right triangle. I'm going to think of this as x over 1. I'm going to draw a right triangle with an angle y right here, so that the sine of that angle gives me opposite over hypotenuse. Opposite side of that is x, and the hypotenuse is 1. And now we're going to find this side because I want the cosine of y. So for now, let me call it a. And a squared plus x squared is 1. I'm going to solve that for a. A squared is 1 minus x squared. So a is the square root of 1 minus x squared. So that goes over here. And now I want you to use that triangle and tell me what the cosine of that angle y is. What's that? Just the square root of 1 minus x squared, because the hypotenuse has length 1. So I'm going to fill that in. Cosine of y is the square root of 1 minus x squared. So what we just found out was that the derivative of the arcsine of x is the square root of 1 over the square root of 1 minus x squared. So put those two together. The derivative with respect to x of the arcsine of x is equal to 1 over the square root of 1 minus x squared. If I had something here more than just a single x, then we have to apply the chain rule. So when I have more than an x, I use the variable u to denote some function of x. So the chain rule version of this is that the derivative with respect to x of the arcsine of u is 1 over the square root of 1 minus u squared times u prime. So that's a new formula for you. You can call them two formulas. One's just a generalization of the other. And so we're going to do it again. If I want to know what y prime is, if y is the arc cosine of x, I write this equivalent statement and use implicit differentiation. I take the derivative of the left side, the derivative cosine is minus the sine of y times y prime, and the derivative of x is just 1. And now I solve for y prime by dividing by minus the sine of y. And we have that. But if I draw a right triangle again with an angle y, giving me the cosine of the angle y is x, I have this triangle here. Put an angle y in there. Cosine is the adjacent side over the hypotenuse. So I'm going to label the adjacent side x and the hypotenuse 1. The same steps in the Pythagorean theorem give me the third side to be 1 minus x squared. And so the sine of y is the opposite over the hypotenuse, which means I have that y prime is equal to, let me put the minus sign on top. The sine of y is the square root of 1 minus x squared. And so look what that says. It says that the derivative of the inverse cosine is exactly the same as the derivative of the inverse sine, except negative. The derivative with respect to x of the arc cosine, another c, the arc cosine of x is negative 1 over the square root of 1 minus x squared. If you remember this, and it's easy to remember, just slap a minus sign on there. So let's do the same thing to derive the formula for the arctangent. Start over there with the statement that says the arctangent of x is an angle y that you take the tangent of to get x. Now take the derivative of both sides. What's the derivative of tangent? So I get secant squared y, y prime. Over there I get a 1. When I solve that for y prime, I get that y prime is 1 over secant squared of y. And what I'm going to do here is draw a triangle with an angle y in it, so that the ratio of the opposite to the adjacent simplifies to x. Tangent is x over 1. Do the Pythagorean theorem and tell me what the hypotenuse is in terms of x. More. Leg squared plus leg squared is hypotenuse squared. So 1 squared plus x squared is the hypotenuse squared. That makes this 1 plus x squared, since 1 squared is just 1. So I need to put the secant of y down here and then square it. Which two sides of the triangle are we talking about to get the secant of that angle y? Whatever cosine, cosine is adjacent over hypotenuse. And so I just lost my train of thought. Cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. So hypotenuse over adjacent just leaves us the square root of 1 plus x squared. But I got to square it. So that gets rid of the radical sign. And so there's the derivative of the inverse tangent of x. The derivative of the inverse tangent of x is 1 over 1 plus x squared. So let me erase that stuff here and put that in a box so I can point to it later. I don't need all these steps. I just want to get the big stuff. So what we have so far is that the derivative with respect to x of the inverse sine of x is 1 over the square root of 1 minus x squared. But the general version of that says that the derivative with respect to x of the arc sine of u is 1 over the square root of 1 minus u squared times u prime. The second thing that we did was show that the derivative with respect to x of the arc cosine of x is just minus the derivative with respect to x of the arc sine. So that's my way of saying I'm not going to memorize that one. Then I want to write the derivative of the arc tangent up here. The derivative with respect to x of the arc tangent of x looks like 1 over 1 plus x squared, or x squared plus 1. Addition is commutative. This one has no square root sign. And so when we do the general version of it, the derivative with respect to x of the arc tangent of u looks like 1 over 1 plus u squared times u prime. Take a wild guess at what the derivative with respect to x of the arc cotangent is going to be.
1 over square root of 1 plus x squared. Or
First, what's the derivative of a cotangent? What's the derivative of cotangent?
cosecant x.
Oh, which one is it?
Cosecant squared.
It's cosecant squared. It's a negative cosecant squared of x. So it'd have a square term, which means it's not going to have a radical sign. It's got a negative with the cosecant instead of the secant. So it's going to do the same thing that this did to the sine. It's going to give us the same derivative as the arctangent, but negative. So I don't need to memorize that one. The arc cosecant is going to have the same derivative as the arcsecant, but negative. So let's derive the formula for the arcsecant. Let me move it over a little bit. So to take the derivative of the arcsecant, which doesn't show up on my board, twist it. So to get the derivative of the arcsecant of x, y is equal to the arcsecant of x is equivalent to the secant of y is x. So now we do implicit differentiation. The derivative on the left-hand side. Now you're going to tell me what the derivative of a secant is. So here it'd be secant y tangent y times y prime. And on the right-hand side, the derivative of x is just 1. So y prime is 1 over the secant of y times the tangent of y. But from this line, the secant of y is x. Now let's figure out the tangent of angle y by doing that right triangle stuff. So from here, I'm going to draw a right triangle with the angle y here. The secant reduces to the ratio of x over 1. Secant is hypotenuse over adjacent. And then just like before, this side's going to be hypotenuse over adjacent. So hypotenuse squared is equal to leg squared plus the other leg squared. So if I'm solving for b, that leg over there is the square root of x squared minus 1. And so the tangent of that angle is opposite over adjacent, which just reduces the square root of x squared minus 1. So the derivative of an arcsecant is 1 over x times the square root of x squared minus 1. So the x squared is in front of the minus sign in this one. The x squared is in front of the minus sign. And so the general version of that with a u says that the derivative with respect to x of an arcsecant of u is 1 over u square root of u squared minus 1 times u prime. Now the arcsecant is kind of bizarre in that, let me draw you a cosine curve here. See if I can explain this. There's a cosine curve. There's a cosine curve. And the cosine is 0 at multiples of pi halves. And at pi, it hits -1. And at 0, it hits +1. So when we made the definition of the inverse cosine, we cut off the graph from 0 to pi. When you look at the graph of the inverse secant, here's the secant graph. Everywhere it has a 0, cosine has a 0, the secant itself has an asymptote, since the secant is 1 over the cosine. And here in green is the graph of the secant function. It has these little bowls to it with asymptotes. Like that. And if we cut off, let me see what I'm trying to say. I don't know what I'm trying to say. Gotcha. Here's where we cut off the graph to define the inverse secant function. We take this piece right here and this piece right here. So the definition of y is equal to the arcsecant of x has these y values to be between 0 and pi over 2, and then between pi over 2 and pi. But these x values were the ones over here. No, I don't want to say it that way. I don't know how I want to say that. Why I want to say. The reason I want to say that is the derivative form has this in absolute value belows. And I can't figure out why. Maybe so that I can draw the triangle. Yeah, that's why. because x is the length of the hypotenuse. And the hypotenuse has to be positive. And so the formula has this absolute value margin. So that's defined in the same way as the other ones. And then we're not going to worry about the derivative of the arc cosecant because it's the same as the derivative of the arc secant, but negative. So in other words, just learn these derivatives. This one, and that one. And then their co-functions, or at least their arc co-functions, have the same derivative, but negative. But if you forget their formula, you can always do this again. You can always do this implicit differentiation step. So 3 more derivatives for you to learn. And let's see if you can find a derivative here. Find f prime of x if, in part A, f of x is the inverse tangent of something. If f of x is the inverse tangent of 10x squared, let's just do that one first. So here we've got a function of x. So we're going to use the general form that the derivative of the arctangent of u is 1 over 1 plus u squared times u prime. So u is the 10x squared. So f prime of x is 1 over 1 plus u squared. So in there, I'm going to put the 10x squared. And then multiply that by u prime. So now I'm just in the parentheses. I'm getting the derivative of 10x squared to be 20x. And then we'll simplify that. Slide the 20x over on the top. Go downstairs and square the 10x squared and get 100 x to the 4th. Good. Okay. Find the derivative of f of x is equal to 6 times the arc secant of e to the 2x. So the formula says you make the ratio 1 over the absolute value of u times the square root of u squared minus 1 times u prime. It's just not moving. So this term is our u. The 6 is along for the ride. So f prime is going to have a 6 here. Then 1 over the absolute value of u times the square root of the u squared minus 1 times u prime. What's the derivative of e to the 2x? Times? So it's 2e to the 2x. Okay? Now, e to the x is positive, so the absolute value bars here are doing nothing. So we don't even need them. E to the 2x is already positive. I can put these three numbers together, 6 times 1 times 2e to the 2x, and get 12e to the 2x. Downstairs, I have an e to the 2x. What do you get when you square e to the 2x? Raise a power to a power. E to the 4x. Let's multiply exponents. And then this is a common factor, you can cancel it. And so you just get 12 over the square root of e to the 4x minus 1. So let me get this out of my way because all I need are those three in the right-hand corner. Okay, so for part C, I want you to take the derivative of the arc sine of the square root of x. So my u is the square root of x, and our formula says the derivative arc sine of u is 1 over the square root of 1 minus u squared times u prime. All right, so here we go. I use the square root of x. So f prime is 1 over the square root of 1 minus our u term squared. And now u prime. Do you have the derivative of the square root of x memorized, or do you want me to write it as x to the 1/2? 1 over 2 square root of x. And so if I square the square root of x down there, I get the square root of 1 minus x. And then I've got times 1 over 2 square root of x. And really, there's nothing to make that look pretty. I suppose you can share denominators, but I'll just leave it there. Okay. Okay, so really 3 more derivative rules to remember. And if you see their co-functions, cosine here, you just slap a minus. A cotangent here, you slap a minus. Cosecant, you slap a minus. But now I want to show you something called logarithmic differentiation. What's neat about logarithms is that they have those 3 properties. That the log of a product can be broken up into the log of 2 terms. The log of a quotient can be broken up in the log of 2 terms. And the log of something to a power can be written as that power times the log of something. We're going to use especially that last one to take the derivatives of things with powers that we don't know how to handle. Like all of us can take the derivative of x to the 10, 10x to the 9. But we don't have a rule that tells us how to take the derivative of 10 to the x. Swap places, put the power as the x and the base as a number. We know how to take the derivative of e to the x. We're going to learn how to take the derivative of 10 to the x. And other numbers to the x. So let's look at using logarithmic differentiation to take the derivative of 10 to the x. If I want to find y prime for y is equal to 10 to the x, and I don't have a rule that says I bring the x down and raise the power to 1 power less. That's only true if the exponent's a number. First, we're going to take the natural log of both sides. So you take that equation and write it as the natural log of y is equal to the natural log of 10 to the x. And the reason we do this is so that we can use that property of logarithms that brings the power down to the front of the logarithm. So now my sentence says the natural log of y is equal to x times the natural log of 10. From here, we use implicit differentiation to find y prime. Take the derivative of both sides with respect to x. So what do you think you get when you take the derivative of the natural log of y?
1 over y, y prime.
Whatever y times y prime. On the right-hand side, I have x times a constant. Natural log of 10 is some irrational number. So what do you think the derivative of x times a constant is going to be? What's the derivative of 5x? 5. So the derivative of x times the natural log of 10 is the natural log of 10. So the next step in the implicit differentiation is to solve for y prime. Here I'm going to multiply both sides by y. But y is 10 to the x. So substitute out the y and put 10 to the x there. So y prime is 10 to the x times the natural log of 10. So let's do it again. Let's change it up a little bit. What's your favorite number? 7. So let's let y equal 7 raised to the, I don't know, let's say x squared power. And let's do the same sequence of steps. Take the natural log of both sides. Our goal is to find y prime. Take the natural log of both sides. Then use that log property that allows us to bring the exponent down in front of the log of 7. So we have the natural log of y is equal to x squared times the natural log of 7. Again, the natural log of 7 is just a constant. Take the derivative of both sides. On this side, you get 1 over y times y prime. Here, log of 7 is a constant. I can just hold it and take the derivative of the x squared. 2x. And then I'm going to multiply both sides by y to solve for y prime. But in the original statement, y was 7 to the x squared. It very much mimics the way we take the derivative of e. The derivative of e to a power is itself times the derivative of a power. But it's got this extra term here, which is the natural log of the base. Same deal here. If I'm taking the derivative of e to the x, I get e to the x back. Well, I got the 10 to the x back times the natural log of 10. The derivative of any exponential function is itself times the natural log of the base times the derivative of the exponent. So as a general rule, the derivative with respect to x of some number, yes. Yeah. This rule is important. I'm going to use a as my number and use my function of x. We get the function back times the derivative of the exponent times the natural log of the base. That fits the derivative of e to the u because the natural log of e is just 1. Okay? Now I use the natural log here instead of a log base 10, but we can derive a formula for the derivative of logarithms other bases as well. These steps also work when I have a function of x down here and a function of x up there. Like if I want to take the derivative of the sine of x raised to the power of x, I do these same steps. Let's do it, and then you'll go. Let's take the derivative of the sine of x raised to the x power. It doesn't follow that rule, but it does follow the logarithmic differentiation. The base is a function of x, and the exponent is a function of x. So we start the same way, take the natural log of both sides. And we do this logarithm thing so that we can bring that x that's the power and put it in front of the logarithm. Now that everything's on one line, we use implicit differentiation. We're looking for y prime, so we just use implicit differentiation through here. On the left side, the derivative is still 1 over y times y prime. On the right side, we need to do the product rule. So I've got the first times the derivative of the second. What's the derivative of the natural log of sine of x?
1 over sine.
1 over sine of x times the derivative inside gives me a cosine of x. 1 over u prime. That's half my product rule. The other half of the product rule is the second factor, natural log of the sine of x, times the first, but the first has a derivative of just 1. Then we solve that for y prime by multiplying both sides by y. If you want, we have a trig function that's cosine over sine. Which one is that? Cotangent. And so we can leave it there, or we can do what we did before, where this y is, we can put the sine of x to the x. Okay? So keep sharp. If you want to take the derivative with respect to x of some function of x raised to another function of x, we don't have a general formula. Use logarithmic differentiation. So I gave you 3 new formulas for your inverse trig functions. This new formula for a number to a function power, and then the technique of logarithmic differentiation to do something like that. And that's all in this one section on implicit differentiation. Whole bunch of stuff. But we'll quit there. So that takes us through section 3.6, I think, is implicit differentiation. Or 3.7. 3.6, and then 3.7 is related rates, and 3.8 is linear approximation. Okay, so I sent you guys a handout through email. We'll do that one on Friday. We'll do related rates, which is more implicit differentiation. But you should have enough to get most of your web work done. So bring me your web work questions for Friday as well. Good? Woohoo!